Hello students, I am Assistant Professor Aparna Kedari and today we are going to study the strength of organic acids and bases. The first is the strength of organic acids and example is propanoic acid is weaker acid than acetic acid. As electron donating groups or atoms decrease the acidity due to plus I effect. Then in this case, in propanoic acid, the alkyl group is the ethyl and in acetic acid, the alkyl group is methyl. The plus I effect of ethyl group is greater than the plus I effect of methyl group, and due to this it makes the dissociation of OH bond difficult in the propanoic acid because it continuously increases the electron density around this carboxylic acid group. Therefore this OH bond becomes strong bond. This ethyl group increase more electron density around this carboxylic group, and therefore this OH bond becomes strong bond. Therefore it is difficult to dissociate this OH bond. But in case this plus I effect is less than the uh, plus I effect of ethyl group, therefore there is less electron density around it. Second, the conjugate base formed after the dissociation. This conjugate base of propanoic acid is more destabilized due to more plus I effect of this ethyl group than methyl group. Therefore, propanoic acid is weaker acid than the acetic acid. Then second example is the acetic acid is weaker acid than formic acid. Formic acid has no plus I effect and therefore its dissociation is more easier than the acetic acid which has plus I effect due to CH3 group. Here is the dissociation of both acids, the dissociation of formic acid and dissociation of acetic acid. In acetic acid, the acetic acid undergo dissociation to give carboxylate ion or acetate ion or conjugate base and plus H plus. Formic acid dissociate to give formate ion plus H plus. Then in this case, this CH3 has plus I effect or exert plus I effect. It increases the electron density around this OH group. Therefore, this OH bond becomes strong and it is difficult to break this bond and to give H plus ion. Also, similarly, it decrease the stability or it destabilize the conjugate base. Here, oxygen is negatively charged, and this CH3 group, which has plus I effect or which exert plus I effect, increase the electron density around this negatively charged oxygen. Then there is greater electron density around this oxygen. Therefore, this easily attack on this H plus and equilibrium shifted more to undissociated form of this acetic acid. But such destabilization is not observed in the carboxylate conjugate base of formic acid because the hydrogen does not show the plus I effect. Therefore, here this conjugate base is stabilized by the resonance and there is no attack on H plus. Therefore, equilibrium is more shifted to the conjugate base, that is dissociated form of formic acid. Therefore, the conjugate base of acetic acid is destabilized due to plus I effect, but such destabilization is not present in the conjugate base of formic acid. Therefore, acetic acid is weaker acid than the formic acid. pK of formic acid is 3.377 and the pK of acetic acid is 4.76. Less the pK value, stronger will be the acid. Then third example is the halogen substituted acetic acids are stronger than the acetic acid. Here, as the minus I effect increases, the strength of acids also increases. All halogen atoms exert minus I effect, that is electron withdrawing inductive effect, and therefore they will help to dissociate OH bond easily, and also they stabilize the conjugate base formed after the dissociation. The minus I effect of fluorine is highest, therefore the fluoroacetic acid is stronger acid than the chloro, bromo and iodoacetic acid because the electronegativity order among the halogen is fluorine is more electronegative than bromine, chlorine and iodine. This therefore it exerts greater minus I effect. Then also minus I effect decreases in this order. Fluorine exerts strong minus I effect than bromine, chlorine and iodine. Here is the dissociation of acetic acid and bromoacetic acid, chloroacetic acid and fluoroacetic acid. Fluorine exerts strong minus I effect, therefore it withdraws electron from OH bond, it assists the dissociation of OH bond, and after dissociation it stabilizes this conjugate base more than this because it has strong minus I effect. Therefore in this order acidity increases, and therefore halogen substituted acetic acids are stronger acid than the acetic acid because such a stabilization is not present in the acetic acid. It destabilizes this conjugate base by donating or by showing this plus I effect due to CH3 group. Then next example is the trichloroacetic acid is stronger acid than the acetic acid, monochloroacetic acid, dichloroacetic acid. The minus I here in trichloroacetic acid pK is 0.464, and here in dichloroacetic acid this pK is 1.3, and in this monochloroacetic acid this pK is 2.8, and in this acetic acid this pK is 4.8. The trichloroacetic acid, that is when there are total 3 chlorine atoms which which exert strong minus I effect, and therefore it assists the dissociation of this OH bond quickly, and it also stabilizes the conjugate base more than these other acids. The minus I effect increase as the number of halogen atoms increases, and it increases the acidity. Therefore, each chlorine increases the minus I effect and therefore contributes in increasing the acid state. Therefore, acidity increases from acetic acid to monochloroacetic acid. Monochloroacetic acid is weak acid than trichloro, and trichloroacetic acid is stronger acid than other three or rest of these acids. Then next example is the alpha chloroacetic acid, butanoic acid is stronger acid than the butanoic acid, gamma chloroacetic butanoic acid. Here this is butanoic acid with pK 4.4, sorry, here is the butanoic acid. Sorry, here is the butanoic acid. Butanoic acid is strong, is a weaker acid than this alpha, beta, chloro and gamma acids. Then as the distance of minus I group or atoms increases from OH group, and the minus I effect goes on decreasing, and therefore its influence in increasing the acidity also decreases. Here in butanoic acid with pK is 4.8 and pK here is the 4 pK is 2.8, and here in beta chlorobutanoic acid this pK is 4.1 and pK in gamma chlorobutanoic acid is 4.5 acid. As the distance of minus I group or atom increases from OH, the minus I effect goes on decreasing because as distance increases, the magnitude of minus I effect or inductive effect is decreases. In chlorobutanoic acid, this chlorine atom is present on the adjacent carbon atom, and in beta chloro it is one carbon away, and in gamma chlorobutanoic acid it is two carbon away. Therefore, the minus magnitude of minus I effect goes on decreasing. Therefore, all these chlorobutanoic acids are stronger acid than butanoic acid because there is minus I effect, and such effect is absent in the butanoic acid. But in case of alpha chlorobutanoic acid, beta chlorobutanoic acid, and gamma chlorobutanoic acid, this alpha chlorobutanoic acid is stronger acid than beta than gamma because it is on the adjacent carbon. Therefore, here it exerts the strong minus I effect, and due to this strong minus I effect, the dissociation of this OH bond is easy, and also it stabilizes the conjugate base more than the this beta chlorobutanoic acid and gamma chlorobutanoic acid. Then next example is the benzoic acid is stronger acid than the cyclohexane carboxylic acid. As the percentage of S character increases, the minus I effect increases, and hence the acidity increases. In this benzoic acid, the COH group or carboxylic group is attached to sp2 carbon, and in cyclohexane carboxylic acid, the COH group is attached to sp3 hybridized carbon atom. This carbon atom is sp2, and here this carbon atom is sp3 carbon atom. In sp2 hybridized carbon atom, the percentage of S character is 33.33%, and in sp3 the percentage of S character in sp3 hybridized carbon is 25%. Therefore, as percentage of S character increases, the electronegativity of carbon increases, and it exerts strong minus I effect than the sp3 hybridized carbon atom. Therefore, in this benzoic acid, COH group is attached to sp2 carbon atom, and while in cyclohexane carboxylic acid, the COH group is attached to sp3 carbon atom. Therefore, it is this carbon is more electronegative. It assists the easy dissociation. It assists the dissociation of OH bond. Also, it stabilizes the conjugate base more than the cyclohexane carboxylic acid. In cyclohexane carboxylic acid, this sp3 hybridized carbon exert the plus I effect. It increases the electron density around this OH bond. Therefore, it is difficult to break this OH bond or dissociate this OH bond. Also, it destabilizes the conjugate base formed after the dissociation. But in case of this benzoic acid, it assists the dissociation of OH bond. Also, it stabilizes the conjugate base formed after the dissociation. pK value of benzoic acid is 4.1, and the pK value of cyclohexane carboxylic acid is 4.86. Therefore, less the pK value, stronger is the acid. Then next is the strength of organic bases. Then base is any substance which donates electron pair to the H plus. Then therefore the base should contain an atom which has electron pairs to donate. The base may be neutral species or it may be negatively charged species. The strength of bases depend on first factor, that is availability of electron pair. Second factor is the tendency to donate electron pairs. And third factor is the stability of conjugate acid formed after the donation. Then base may be neutral species with electron pairs. It attack on H plus and it gives conjugate acid. Here this base using its electron pair, therefore in this case in conjugate acid this base acquires positive charge, or this B atom acquires positive charge. And then in this second example, this base is negatively charged species, therefore it uses its negative charge or to these electrons to form bond with this H plus, therefore it is neutral conjugate acid. The first example is the methylamine is stronger base than the ammonia. In methylamine, the plus I effect of methyl group increase the electron density on nitrogen as compared to ammonia, because in ammonia there is no such a group present which increase the electron density around nitrogen, and hence donation of electron pair is more easy, and the positive charge on nitrogen in the conjugate acid stabilized due to the plus I effect of C3 group. Such a stabilization is absent in the ammonia, this NH4 plus, that is conjugate acid of ammonia, because here there is no such group which decrease or increase the electron density around a nitrogen, positively charged nitrogen by plus I effect. But in this case, this methyl group exert plus I effect, it increase the electron density around nitrogen, therefore more electrons are available to donate, and once the conjugate acid is formed, it is well stabilized by the plus I effect of this methyl group, because it increases the electron, or it stabilizes this positively charged nitrogen by increasing electron density around this nitrogen. But such stabilization is absent in the conjugate acid of ammonia. Therefore, the methylamine is stronger base than the ammonia. pKa value for methylamine is 10.6 and pKa for ammonia is 9.24. Therefore, less the pKa and less is the base strength. Then next, all types of ammonia. This is ammonia, then primary amine, secondary amine, tertiary amine. As the number of R group increases, the plus I effect should go on increasing, making tertiary, and this makes the tertiary amine more strongest base than the primary and secondary amine or than ammonia. Therefore, order of inductive effect in tertiary amine is greater, because there are three alkyl groups which increase the electron density around carbon, or there are three electron donating groups. Then in secondary amine there are only two groups which shows plus I effect, or that is electron donating inductive effect. In primary amine there is only one alkyl group which increase the electron density around nitrogen. Therefore, expected order for basicity in among this ammonia and primary, secondary, tertiary amines is tertiary amine is stronger bases than the secondary amine, than primary amine and ammonia. Then the pKa values, here is the pKa values of different amines, primary, secondary and tertiary amine. When this R group or alkyl group is methyl group, then the primary amine pKa value is 10.6, pKa value is 10.8. In secondary amine, that is two methyl groups on this nitrogen, here 9.8. When the alkyl group is the ethyl group, then this primary amine is 10.10, in secondary amine 11.0 and tertiary amine 10.7. In N-propyl, when the R group or alkyl group is the N-propyl, then this primary amine is 10.7, in secondary amine 11.0 and in tertiary point the pKa value is 10.3. Then when the this R group is N-butyl, then 10.7 is the pKa, 11.3 and 9.3. And from this data, we can conclude that the all amines are stronger bases than ammonia, because there is greater electron density around nitrogen, and by donation of electrons. And then all primary amines are weaker than the secondary and tertiary. Secondary amines are strongest bases than the primary and tertiary and ammonia. The tertiary amines are stronger than primary amine, but they are weaker than the secondary amine. The tertiary amines, even though has highest plus I effect, because there are three alkyl groups around the nitrogen, but their basicity is slightly less than the secondary amine, and this indicates that basicity is not only depends on the availability of electron pairs, but also it depends on the stability of conjugate acid form. Here we see the stability of conjugate acids. Then conjugate acids solvated by water in case of primary amine, secondary amine and tertiary amine. Then water through this conjugate acids of this all primary, secondary and tertiary amine is stabilized by the hydrogen bonding in water. Then the solvation in case of tertiary atom is least, because here is the only one hydrogen which solvated by, or this tertiary conjugate acid of tertiary amine is solvated by only one hydrogen atom. Here there are in secondary amine there are two hydrogen atom which undergo solvation by water molecule, and here in primary amine here three hydrogen atom. But in secondary amines are strongest bases because here these hydrogens are two for solvation, as well as here there are two alkyl groups. Here only one alkyl group. Therefore, the secondary amines are strongest base than tertiary amine, and tertiary amines are strongest bases than the primary amine. Then next is the trifluoromethylamine is found to be totally neutral compound due to the very strong minus I effect of 9 fluorine atom. This all 9 fluorine atom exert strong minus I effect. Therefore, this electron pairs on nitrogen continuously withdraw by these three fluorine atoms, and therefore there are no electrons are available for donation. Therefore, this compound, that is trifluoromethylamine, is neutral compound. This is all about the organic strength of organic acids and organic bases.